Welcome to another show. Welcome to Victoria Station, the science capital of the free world. And today it's going to be a very interesting show, a little bit longer because there is a lot to cover. And today it's going to be all about gravity, mass, the field of mass of the whole gravity of the galaxy, and dark energy. First, I thought to point out, which is interesting, is dark energy and dark matter. Scientists knew that there is it in the universe because there is evidence. The galaxy shows as it rotates, it shows that there is matter, but people can't see it. And the reason why they can't see it, they call it dark matter. But the reason why they can't see it is because it's dark. When it's dark, a telescope doesn't pick it up, basically, which is the explanation. A telescope sees when something light bounces off it or it gives light. And another big explanation that's going to be today is dark energy, the whole explanation, equations about it and everything in the universe, how it moves galaxies and so on. Now, the big deal about these two forces is, and my physics totally explains them and knows precisely mathematically through equations what they are, even the speed of them and everything. Dark energy is actually the beginning and can give us Star Trek. Dark matter, that's what I explained in previous shows. In part, that's just the cold or graphene, the cold energy our skin is missing and everything. Now, the big problem with physics and science in the past was many scientists around the world, you ask them, what's darkness? Oh, darkness is just nothing, you know, absence of light and things like that. Like saying darkness is absence of light. That's like saying being dumb is absence of being smart. Or when it's cold, you say, oh, it's cold, oh, that's absence of heat. If you say cold is absence of heat, then that means you don't have a clue what cold is. You just know what heat is. And then you explain cold by mentioning something else. But that's totally not correct. And darkness, dark matter in space is just the cold matter I mentioned. Like when I explained nukes, when you see smoke from a nuke, that's dark matter. When you see fire and heat, that's light matter. So even in space, dark matter, and that's the matter we need to give us life and to live long, that's the same type of matter. Of course, in space it is different. In space, a black hole, when a planet falls into a black hole, it cannot turn into energy because darkness does not blow up. A light blows up, heat blows up, energy, that's E equals mc squared, blows up. So a sun falls into a black hole, it comes out as subatomic particles, energy, radiation, and it just comes out. But when dark matter falls into a black hole, it condenses. Or when it's spinning around the black hole, that's how antimatter is made when it's hot matter, but it also happens with atoms, individual atoms of cold matter as well. And there too dark matter is made. But basically, when something falls into a black hole, it's squeezed so much that a planet could be turned into something 100 times smaller than the whole planet. And then it's all crushed into individual bits. And when they are small enough, the black hole, depending on its size, carries them out with its outgoing masses. Plus it has gravitational waves, so it can pick up even bigger parts of it. So dark matter in space is just the cold matter I mentioned, but highly, highly dense, squeezed by the masses of black holes extremely, extremely much into extremely dense pieces of matter. And then the galaxy gets tons and tons of dark matter. But black holes make dark matter, simply put, that which is just the beginning part of that and everything. So this is the universe, one can say. This is now individual galaxies to themselves. I'll just stop that for a second to explain. And let's say 3 galaxies are right here, although these are a bit far away because the light is fainter, this one's closer because the light is bigger. That's how telescopes see. But they were like on a sheet of paper, dark energy can be explained very, very easily. 1, 2, 3 galaxies are right there, 1 is there, and 1, 2, 3, 4, 5, let's say, are on this side. So dark energy is just outgoing mass of each individual black hole center of galaxy. A black hole that's the center of a galaxy is the most massive, the hugest, strongest individual piece of existence in the whole universe. So there's nothing bigger than a black hole that is an individual piece to itself of something. Although a black hole is just is not a piece of matter. It's more like something that's a force, but it is a place, a real place. So, because forces are invisible, gravity is invisible, and the mass is invisible, and they move things and give them mass and effect on them and everything. But a black hole is like that, but it sucks things in, so to speak. So those are black holes right there, and the outgoing mass of these 5, let's say, and there are 3 on this side, are going to hit that one. Although these are a bit closer if they were all on a straight place. But these are probably closer to it because these are fainter, so back, in the back they're further away and everything. But if it was just these galaxies I mentioned, 5 dark energies are hitting this one, and 3 dark energies are hitting it from this side. So it's then all about geometry. It's like a force. Dark energy is a force that comes out of each galaxy and slams into this one. And when it hits it, all 5 of them, it'll probably go this way, exactly. This galaxy will go that way. Now these 3, if they were just as big right here, they would hit it, so that force will slightly make it go that way, but since here there are 5, then it would go slower this way. But that is the beginning explanation, and there people can see how all that is extremely complex, because in the universe there are billions of galaxies, and it's not that easy to calculate the distance from each one and so on, but a computer does that, of course. A computer can show the effects of dark energy very, very easily. So these 5 dark energies are hitting this one, and these 3 are hitting it. So that means it'll go this way. It'll move that way from that geometry point of view. But the dark energy coming out of that galaxy, this one, gives mass to all the billions of suns in it. Then once it leaves the space of gravitational space, then it speeds up. And that, in part, dark energy, through the galaxy, if we tap into that mass, know how to do it scientifically and through matter, that gives us Star Trek to go around the galaxy then on that force, on a real force. Now, we can mention Einstein. Einstein called that curved space. He called that curved space-time. But these explanations that will follow are a lot better and more advanced and more correct and everything. So I'm gonna go into the equations first and then return to this and explain how they all have an effect on the galaxies and everything, all the matter in the galaxy and so on. The equation, there is a lot of them about this. I have hundreds of them, but I have picked like the 30 best and fast. I'm just gonna go through them quickly so that people know the physics of it, and then I'll return to this and explain how the galaxy works and everything. So what I meant to say with that, dark energy, dark matter, and darkness are the 3 things that almost all scientists on Earth say they do not know what it is. But those 3 things can give us such greatness and such great things that it's like beyond comprehension even. Darkness and dark matter can give us life for thousands of years. Dark energy can give us Star Trek and the whole galaxy. And people can there understand how those things are very, very important, but how they eluded science in the past. And most scientists would say they have no clue what it is and something. But now when people understand thoroughly what they are, then that gets a huge, great revolution and very, very great for science and for advancement, for going forward in physics, in technologies and everything. Especially in food and medicine and everything. So I have to bring the camera close like this so people see the equation that I'm explaining, that they can see the whole equation. It is in Serbian, but people can of course translate it if they like, but the equation is in part understood in English as well. So this is the first, as the book goes in the beginning, this is the first formula. It is about the movement of gravity and the reaction of matter that happens inside a gravitational field. So this is sort of also through Newton's physics, but a more thorough explanation of that Newton's law. For every action there is an opposite and equal reaction. Well, this is through that, but a more big science and explanation of that through Newton's law. So the action of movement, which is gravitational space. The action equals movement, which equals gravitational space. The action of movement, of course, is planets, moons, suns. So gravitational space moves matter. So comets, moons, suns, planets, that's what it means. That's what gravitational space moves. Everybody knows that. So that is divided by, the gravitational space movement of it is divided by movement through matter. It is movement through matter, which equals acceleration. Acceleration, of course, is speed, where the matter is and everything. So times that movement of matter, which is the matter itself moving, which gravitational space, of course, moves it and gives it a certain speed, which is acceleration, times that one gets in incoming mass through gravitational pull. So our gravitational pull of planet Earth is just incoming mass. Gravitational space moves the planet, and through that movement and that special acceleration divided by 3085, you get the 9.8 seconds incoming speed of gravitational pull. So that's incoming mass through gravitational pull, which equals incoming mass through infinity of gravitational space. So in gravitational space, there is infinite mass. Mass can go on forever. And that equals the core of the planet through, gravitational pull equals incoming mass through infinite density of the core through the heaviest element in the universe, which is neutronium. So every planet, every moon, every sun has the heaviest neutronium element in it, which is the center of it. Comets do not. Everything that turns around itself, which is the moons, the suns, and the planets, they must have neutronium in the center of them. Because only neutronium can transfer incoming mass into outgoing mass. Lava can't do that and so on, because it's a liquid, and the mass would squeeze the lava densely. If it's a flowing liquid, then that's not happening. Because in the core, the infinite density, the core of a sun, of a moon, of a planet, infinite density of mass means that the mass is 1,000, 1,000, 1,000, 1,000, depending on the geometry, times denser. Because if there's this much mass and it's spherically coming into matter, then at the center point, all that huge mass turns into tiny little place of mass, where the core is. So all that mass condenses into a little space. So it's 1,000 in sun's million trillion times stronger and stronger. Denser mass, therefore. So that action through the core and everything, the acceleration of matter, this is sort of an explanation of how mass comes into matter. That equals the reaction in the whole universe, in suns, in moons, in planets, and so on. And the reaction is the movement of sight through energy, which is divided by outgoing mass, which equals acceleration divided by the size of the particle, because that's energy, size of the particle through for all energies. So, outgoing mass moves all energy: darkness, light, radiation, smell, sound, GPS signal, phone signal, satellite signal, internet signal, radar, so on and so on and so on. But when it is energy through which sight moves, when it is energy, that is for all energy, it is all divided by the size of the particle. So how big is a photon decides how fast it's going to go. How big is a radiation particle in space decides how fast it moves. So outgoing mass equals acceleration always divided by the speed, the size of the particle. So darkness is faster than light because it is smaller particles, simple as that. And of course, tests explain that and everything. Tests can prove that, of course, and everything, and have proven in the past. Radiation is, of course, a lot slower than light because it is a bigger particle, heavy as atoms some. Then sound is slower. Sound is more like sort of information and some things. But outgoing mass equals acceleration that is always bigger than the energy itself. And then that acceleration divides into the size of the particle. Simply put, the smaller the particle, the faster it goes. The bigger the particle, that's energy, the slower it goes. So, and that is for all energies in the whole universe. And times that one gets sight. That sight, which is divided by the size of the picture through distance, times the matter through energy, times the fastest visible force in the universe. So the force of sight is divided by the size of the picture. So the smaller something is, the further away it is. That means through distance. So the size of the picture that the universe is sending happens through distance. So the smaller the picture, the further away it is of a galaxy. The closer, the bigger the picture, the closer it is. That's telescopes and that technologies and so on. But that happens times matter through energy. Sometimes supernova explodes. So that's tons of matter and energy turning into energy. And then a supernova explosion outshines the entire galaxy. So still that force, the size of the picture through distance, happens times matter through energy. So a supernova explosion, telescopes, we see it more than the whole galaxy, some faraway galaxy, because the energy outshines the size of it, of the matter exploding, and the energy is bigger than all the other suns in the galaxy. And that all happens times the fastest visible speed in the universe, which is like, I don't have an exact number of it because I didn't have the proper tools to get it, but it's like faster than light millions and millions of times. So that's that equation right there. People can see it. I can zoom in just in case that people see the whole equation and in detail and everything. So the next one is a simple one. I have two of them. This is sort of the same thing, just it is incoming mass, that's gravitational pull into all suns, moons, and stars, equals outgoing mass. So the bigger the matter, the more incoming mass it has. So of course the sun has the biggest ones. And then that equals outgoing mass. See, let's say if you're looking at let's say a satellite is looking at us from space, it can see all of us very easily. But a satellite cannot zoom in to see a neutron. Why? Because incoming mass of a neutron equals its outgoing mass. And they are very, very tiny in the quantum realm. The incoming mass of a neutron is in the quantum realm, and the outgoing mass of it doesn't really go that far. That's in like meters, a few meters is the outgoing mass of a neutron, but it all happens times acceleration in the whole universe. So that's why we cannot see small things. We cannot see an individual atom because its outgoing mass is too small. But a sun we can see very, very easily because its incoming mass is huge, so is its outgoing mass. That's why we can pick up with telescopes distant galaxies, because suns are extremely huge incoming masses and outgoing masses. So that's how it works in the universe. But that all happens times acceleration. Let's say sometimes the sun is moving too fast. It moves through some flux of masses, some joining of masses that was not that was sort of different. It moves through some field of mass that is sort of a little bit different, and its acceleration increases, and that's how a supernova goes off. And then, so if the acceleration is too much, a sun goes supernova. But because of incoming and outgoing mass. So that'll be explained in the future videos all about supernovas. This is one about matter, and just to zoom in on that equation, that's incoming mass equals outgoing mass times acceleration, because acceleration decides incoming mass. So that will all be explained more and more in the future videos. So this is one about energy when it leaves matter. That's all sunshine, darkness, radiation, and so on. Radiation is not an energy because it's not that dense. It has a lot less particles. They are bigger, but a lot less of them coming out, because radiation is a small piece of matter compared to a sun or a planet and so on. But it's about light, darkness, and everything. Everything that has a shadow, that's darkness coming out of it. So energy equals acceleration divided by the size of the particle. So that's important in physics to know. All energy in the universe equals the speed by which energy is moving divided by the size of the particle. The small ones go faster, the big ones go bigger, and that's for all energies in the universe, times the size of matter through gravitational pull, which equals mass. So the bigger the matter, the more energy there will be, of course, through gravitational pull and mass, because they are then bigger as well, and then there will be more energy. So bigger suns shine a lot more energy than smaller ones, of course, a lot more light and everything. And that equals distance of energy, which equals a sphere. So the size of matter and the gravitational pull and mass equals the distance, how far the energy will go, and energy is always a sphere. All darkness, all light in the universe that comes out of matter are spheres, planets, moons, suns. We have a sphere of darkness on Earth. Just the light of the sun makes it disappear, so simply put. So all energy is equal a sphere, and the size of matter decides their distance. Scientists believe that energies go like from Andromeda galaxies to us, but that's totally incorrect. Energy of a sun only goes in the solar system. After that, it's just an image of light that the outgoing masses carry. The energy, which is light, let's say from a sun, A photon cannot exist in cold space. As soon as and as the energy moves, equaling a sphere, it's less and less and less and less dense. When photons are packed together, that's in all sunshine in the universe. When the photons are packed together, that's heavy light. We can see a lot. That's why when you see the sun around it is like, it seems a lot of light. But as the light comes to us, the light is less and less dense. So once the distance of energy, let's say it leaves the solar system, there is no more heat from the sun. And all the photons disappear. When we see a distant star, we do not see photons of it. We see a live image of it that outgoing masses carry. Like right here, this image. You do not see the photons coming out of this TV. You see an image of them when you observe after this video. But these actual photons coming out of this TV, you don't see them for real. So, of course, that's understood. So when we see a distant star, we only see a live image carried by its outgoing mass. But that's a whole butterfly effect. That's a whole different text that will be explained about suns and supernovas. That's called the butterfly effect, I call it in my book. How the energy quantum distance of photons is more and more and more. Then in the end the omega effect happens. They just die off. Once they come into cold space, that's a sphere of energy, the photons cannot go through cold space. They just disappear and die. And that's the energy of a sphere. So distance is decided of the energy of sunlight darkness. It's decided by the size of matter. So the bigger the sun, the further its light goes. But that's in the solar system. After it leaves the heat of the sun, photons cannot go any further. And that is divided by the element of heat, which equals quantum entanglement. Just a second. Yeah, that's exactly what I thought it was. So the distance of energy, which equals a sphere, is proportional to the element of temperature, which equals quantum entanglement. I'm using the sun here, but this is for all matter, an explanation, because all matter has energy. Everything you see on the planet that has a shadow, that's just its cold, dark energy coming out of it, basically. We have nighttime, that's the cold, dark energy coming out of planet Earth, in my physics, and which is explained. So the element of heat is equal to quantum entanglement. Our planet on the surface is cold and dark, and that's temperature, which equals quantum entanglement, and the elements which make up the ground, carbon, and so on, which are dark matter, just like I explained about the plants and everything. We are dark matter, the planet is, the ground is, the trees are, so on, the buildings, the rocks, and everything. That's mostly temperature, cold temperature, that equals that quantum entanglement to every individual piece of matter on Earth. When it's a sun, it's the neutronium quantum entanglement of the center of the sun, and that's the element of neutronium there with some electrons, and that gives the heat that makes the light and the energy of a sphere. So to explain that fast and quickly, so I'll zoom in on that so people can see it in detail. And okay, so this is a quick explanation about time and gravity. Einstein said that it's curved space-time, but once people understand mathematically and through physics correcter explanation, then it's a lot easier to understand. So that's what this is, in part, a short just explanation of that, because it is part of space and gravity and everything. gravity, G equals speed times space. So the more space there is, the more speed there is in gravity. People all the time examine speed, but they do not take into account, some people, the space that is going through. Like a sun that goes around the black hole that's near it and the one furthest away. Yeah, they do the same circle around the black hole at the same exact time and at the same exact speed in gravity, but not in space. In space, the sun furthest away from the gravitational center goes through 100 times maybe more space than the one nearest to a black hole. That means the speed of it is a lot bigger actually, and it gets more mass and everything. But this is just to start that. So gravity equals speed times space. So gravitational space is identical to time times speed through space. So speed through space is very important to understand time, because speed through space even affects the clock. Because speed through space decides, and the space decides how mass goes into the clock. And mass slams into electricity, slams into the atomic clocks, into the atoms and everything, and affects how they tick and so on. But the difference in ticking of clocks is not at all in space. As far as space-time, it doesn't have anything to do with space-time. It's just the speed through space which decides the speed of incoming mass divided by 3,085, and then the incoming speed of mass affects how the clock ticks. So gravitational space equals time times speed through space. So that's how one also gets speed through space. It is decided by gravitational space and how big it is and so on, what it's coming out of. So right here is a simple explanation. The universe through space equals distance. Now that's about the whole universe. The entire universe in my physics is mass, what I just explained. To simply understand mass, gravitational pull. People call it gravitational pull because that's how Newton called it, so we call it gravity gravitational pull, and I agree with Newton, of course, about the name. Of course, we should call it that. But the whole universe is mass. Gravitational pull is just mass. Gravity, I see it as the force moving matter, but mass is what the matter is moving through, so to speak. And gravitational pull is what we are moving through, and that's the field of mass. So the universe through space equals distance. This explains the whole universe equals distance. Of course, it's some distance we can't even write the number down or even see it or know it. It's too big, of course, but that's like a simple explanation about the whole universe. The universe equals space, which equals distance. The universe through space equals distance. Further explanation of that, the universe divided by space equals distance, which is divided by space, which equals forces, matter, energy through time. So the entire universe has in it forces, that's gravity and mass. It has matter in it, and it has energy in it through time. And that all happens through time, although time is, in my physics, is a math. Is like software inside gravity, but physically it's not a real physical place. So it's an idea more. The time is more like an idea, so. People can see that clearly. So next about the universe is equal distance divided by space through time. So that would be a mathematically correct explanation. The universe equals distance divided by space through time. This is sort of like mentioning Einstein. But space here is mentioned as distance, not as the fabric of space. The fabric of space, I see it as completely and understandably nothing. You have a fabric of space right here. A square meter of space is right here, like everywhere. Now, let's say a person took, let's say, on the North Pole, in a square meter of space, he put all the nuclear weapons into it and exploded them. It could not damage, or all the supernovas even in the universe, into 1 square meter of space, and they all exploded. It could not damage a centimeter of space itself, the fabric of space itself, because space itself is unseeable, untouchable, ununderstandable, undestroyable, unchangeable. Nothing alters it. So nothing in space can alter the fabric of space itself. So it is the ultimate nothing, space itself. But it has a lot of stuff in it, therefore. But of course it's not nothing, it is something, of course, but something that is undestroyable, unchangeable, unseeable, unfeelable, ununderstandable. So the universe equals distance divided by space through time. The universe equals distance divided by forces through acceleration, which equals time. So gravity is a force. It gives acceleration to matter, and that equals time. We have 356 days. If we were on Pluto, which has different acceleration, there'd be like thousands of days and nights in 1 year, so to speak. So those are also equations about it. This one could be told. Universe equals space, which equals outgoing mass divided by energy proportional to outgoing mass through matter. So the energy comes from outgoing masses from matter. That's light, darkness, and they fill the entire universe. They fill the entire universe, energy that comes out of matter, because all of space has light or darkness in it. All of space. Which satellite footage, of course, shows as well. Okay, so this is one about how things are seen in the universe. So the visible universe equals outgoing masses. I mentioned them earlier. People now probably know what I'm talking about. The visible universe equals outgoing masses through sight, not through energy. Let's say energy from a sun. We see a star up in the sky. The energy is right there. You can see the energy of the sun. It's like that big when you see a star in the sky. That's because all the energy is there. But the scientists are telling us, oh, the photons of that come here into our eyes, and we see it. Like, come on, who can believe that? We can see the energy is like that big, you know, where people are not blind, okay? So that means that's evidence. All the energy of a star that we see from Earth is way, way far away from us. All we see is outgoing masses and the images they show us, which are live images, of course. So the universe equals outgoing masses through sight. And that's how we see a star. That's the force of sight, which is carried by outgoing mass of that star. And that's the whole visible universe is like that. Where there is, the whole visible universe is like that. And that outgoing mass through sight divides into matter times energy through gravitational space, which gives it incoming mass times acceleration, and that whole process gives the fastest visible speed into universe, which is sight. That's how we see galaxies, suns, moons, telescopes. That's exactly how they see. That's a whole explanation of that. So that explains how a telescope sees and everything that it sees and so on. Of course, in that outgoing mass, which carries side, there is a lot of information as well, which also is evidence that it's information. There is blue shift, red shift, sort of figuring out of temperature when people observe faraway stars, galaxies, and so on. So this is one also that explains the universe. The invisible universe equals space times the forces in it. So the entire universe, invisible one, that's mostly gravity, dark energy, and mass, and dark energy is just outgoing mass. The invisible universe is all of it filled, the whole universe, which equals space in it times the forces in it. So, but there is many different ones of them. So, okay, so now this goes into Newton's gravity. Newton said force equals mass times mass divided by distance. That's Newton's distance squared. So that's Newton's law. Newton's equation of gravity, sorry. That's Newton's equation of gravity. Just to see where, yeah, okay. So I'll just explain this one. This is about planet Earth now. Gravity and Earth's gravitational pull. So acceleration of gravity through the solar system, acceleration through the solar system, which equals 100,008 kilometers per hour, that's planet Earth going around the sun. Proportional to that, we get gravitational pull. That's our gravitational pull that makes us stick to the ground, 9.8 meters per second. That's the element of mass, which equals 9.8 meters through a second squared through the Earth. And that gives the weight to us, to all of us. It gives weight through acceleration, which equals gravitation, it's very complicated. Okay, weight proportional to the pull of planet Earth. So that means weight of all things on Earth through acceleration and speed. It happens. Pull is actually, its speed is decided by, it decides the weight of things on Earth and people and so on. Acceleration equals gravitational pull, which is a sphere. That sphere comes from the size of the planet. So any size the planet is in space, it shows its gravitational pull. Our gravitational pull is very, very high up because matter is very, very high up. People should know that as well. Very, very high up where the ozone layer ends, that's all matter. We inhale oxygen. Matter is not just the ground. The entire atmosphere is also matter and the top of the ozone layer. So there gravitational pull starts. Where there's matter, that's where gravitational pull starts to squeeze the planet. So acceleration equals gravitational pull, which is a sphere, but that sphere is decided by the shape of the planet, but it's a sphere on top. And times happens outgoing mass, which equals the gravitational pull, because gravitational pull through the core, through darkness. So that's our planet. The gravitational pull of our planet equals outgoing mass of our planet. So how big our planet is, that's how big the outgoing mass is going to be. Because gravitational pull, how big it is, that's how big our outgoing mass of our planet is, and it carries darkness. And that decides how far away someone can see us. If there are some aliens, looking around, our outgoing mass of our planet decides how far in space it goes. And it decides how far away someone could see us, basically. So that's that. Now, this is a universal explanation of all gravitational pulls of all planets. Acceleration equals speed squared through the solar system, which equals a sphere. Every solar system is a sphere. So where the planet is decides its acceleration and speed. But in all solar systems, that's different. It's not like the sun. Some planet could be very far away, but it's moving very, very slowly. But that's probably because the planets closer to the sun move faster, the ones far away move slower, but far away there is a lot more space, so they're moving also very, very fast. That's just a new math that will be thoroughly explained to calculate every gravitational pull of every piece of matter a clock there is, even to measure it and so on. So which equals a sphere, which equals gravity, so that's gravity. Proportional to that is acceleration, which equals speed squared through gravitational pull of every planet, which is the element of mass. So every gravitational pull of every piece of matter in the universe is incoming mass, so that's mass. And that equals a sphere. Mass is always a sphere. In black holes, suns, moons, stars, even in comets, but in smaller pieces of matter, let's say like us, our mass is exactly the shape of our body. But mostly suns, moons, planets are spherical because that's how mass is squeezing them, basically. But when it's smaller matter, it's not all a sphere, it has smaller. But this is about gravitational pull. Gravitational pulls, therefore it's most of them are spheres. Because that's of planet, moon, suns, and so on. Of planets is this one, sorry. So that divides into distance, plus or minus from the gravitational center, which is the sun. So the acceleration and speed and gravitational pull, the speed of gravitational pull and mass is all decided by distance plus or minus to the gravitational center, which is the sun. So if a planet is closer to the sun, it has faster gravitational pull and mass because it's moving faster. But if it's further away, it's moving through a lot more space. So a planet further away from the sun could even have faster gravitational pull and mass when that map is done properly. But for each planet, one would have to know the exact acceleration and speed and how far away it is from the sun, and then he would divide that speed by 3,085, and he would get the exact speed of gravitational pull on that planet. So just what an astrophysicist would have to know is from the sun how far away the planet is and how fast it's moving. And then he knows the exact speed of gravitational pull and mass on that planet. And that's a huge, huge new math explanation that gives us a lot better understanding of the universe and everything, planets and moons and stars and so on. So there is one more equation about that and acceleration of a planet equals acceleration of mass. But here it's not about speed. How big a planet is, that's how much matter is accelerating. And then that identically equals acceleration of incoming gravitational pull. So in size, the acceleration of a planet and the incoming acceleration of gravitational pull mass, they are in space, in size identical. So exactly per atom they are identical. Atom to atom they are exactly the same. So gravitational pull right there, which is incoming mass into a planet, equals the acceleration of matter around the sun, which is a planet, times infinite, to see what that is, times infinite distance. So times infinite distance here, the acceleration of a planet around the sun and the acceleration of incoming gravitational pull, which are the same in size, it happens times infinite distance. So a planet could go around the sun forever, basically. That's what in this equation it says. So let's say stars blow up. A planet could even blow up. Some planets, very hot, close to the sun. Although that doesn't happen, it has not been observed or recorded. But theoretically, you know, some very, very hot planet might blow up. But as far as acceleration of mass and gravity, it can go on forever. The distance, how many circles the planet is going to do around the sun, can go on infinitely, forever. Newton said anything that moves will move forever. But even if a planet blew up, all the subatomic particles would remain of it, and they would still be moving. So that's Newton's law, so to speak. What moves will move forever, basically. And that is divided by distance from the gravitational center. So both the acceleration of a planet and the acceleration of gravitational pull, the speed of both of them, are decided by distance from the gravitational center, which is the sun, of course, that moves the planet in the first place. Every sun has a gravitational center in it. When a sun blows up, then you get a black hole. But when a sun is intact, I call it in physics a gravitational center. And that gravitational center attracts planets to go around the sun, and mass comes out of it. And no, mass comes out of the Newtonian core. But gravity comes out of a immature black hole that's inside every sun, basically. And that's what moves planets, not attraction of matter. Matter cannot attract. If matter attracted each other, they would slam into each other and blow up. And some scientists say that it's attraction of matter and curved time-space. That's really dumb stuff. Has nothing to do with... I mean, this is a far better and more correct explanation. I mean, attraction of matter. Gravity is a force, and it has a center that it comes out of. Black holes are proof of that. So, black holes, if a planet comes near, they will also spin it around them. People know that from evidence and everything. So this is like a fast explanation of, to go further, the acceleration of a planet equals the speed, and proportional to that speed one gets acceleration of gravitational pull, which equals its speed, and that is all divided by the gravitational center that force gravity is coming out of, and divided by distance. So how distant the planet is from gravitational center, which is in the sun, that decides the acceleration of a planet, and divided by 3085, it decides the acceleration of gravitational pull on the planet. The exact speed of both are decided by the distance from the sun, basically. And another fast explanation equation about that is acceleration of our planet equals 108,000 kilometers per hour, and that divides into, by 3085, it divides into the acceleration of gravitational pull. That's what pulls us down to Earth. That equals 9.8 meters per second, and proportional to that, one gets weight of all matter on Earth. One gets weight divided by the size of matter. So if somebody's fat, well then of course he has a lot more weight, because there is more matter that the gravitational pull is attracted to, hits it. So of course, so the size of matter also decides weight, but all these things as well. And that is identical to the gravitational center divided by distance. So that is decided by how far we are away from the sun, to easily explain it, basically. So how far away we are from the sun that too decides how much we weigh, basically. But also the size of us, how big we are, and so. So what I just mentioned about space, thought to continue, we live in a universe where nothing can change or alter the fabric of space itself. So we live in a universe that space itself, nothing can have an effect on it. So nothing in the universe can have an effect on the universe. And that's why, to me, can have an effect on not the things in the universe. We can affect the things in the universe, but we cannot affect space itself. That's what makes it so great and powerful and unknowing, that nothing can change it. We cannot even know what it is, or see it, or feel it, or touch it. We can, the forces in space, the matter in space, even time, we can sort of, the idea of it, experience, but space itself is unchangeable, basically, so to speak. And then we understand that we live in a universe that's sort of, that one part of it is beyond us. What it is, what it actually is, where we actually are. We are in a universe that the fabric of space itself, the space just means space. In old English, you know, space is space. Girls say, I need my space. That, that just means she doesn't want somebody to be around or something. But actually, space itself, that's what it is to me in my physics. Totally beyond human comprehension what it actually is. But nothing can change it or alter it, so, or mess it up, basically. If you took all the supernovas into one square meter of space, you cannot damage it or blow it up. Because even in space, a supernova is something, the space is beyond it. It cannot affect it, and so on. So now this is about in the gravity of the galaxy. And a simple equation about all suns. The speed of all suns, which means for all, the A under is for all, speed of all suns through time equals the gravity of the galaxy. But this is about the idea of time, because every sun will make a circle around the center of the galaxy at the same time. That's what astrophysics says. But in space and mass, in the field of mass, masses are million, billions of them different, and so on. But this is one just to mention time and how gravity affects things. That's in the gravity of the galaxy. So time in the galaxy is identical to the gravity of the galaxy, its speed, and so on. This is one easy, fast explanation of supernovas. That is part of the galaxy and space. So supernovas equal incoming gravitational pull. Supernova equals the intensity of incoming gravitational pull. So the stronger gravitational pull squeezes the sun, that's what causes supernova. And that incoming gravitational pull divides into times one gets the space, which equals incoming mass divided by acceleration through space divided by distance. So the space times space, which gives that intensity of pull, which is then equal to the intensity of mass, which happens by acceleration through space, which the matter of the sun is, which is the space of mass, and that divides into distance from the gravitational center, which is the black hole, the center of a black hole. So where a sun is in the galaxy, how far away it is from the sun, that's the distance. That decides the intensity of incoming gravitational pull, which is incoming mass and its acceleration through space. And that gives a supernova. When gravitational pull squeezes the matter of the sun too much, the neutrons in the core of the sun, they become too tight. They're like squeezing and they don't have anywhere to go anymore. And the more they squeeze together because of intensity of mass, gravitational pull, the hotter and hotter it gets. And sometimes it gets too hot and the sun blows up. This is one fast explanation, but there will be a whole one video just about supernovas, the exact math, quantum distance of neutrons and everything that explains it, a correct, proper physics about that. And that explains the whole supernova happening and everything. So this is one equation, just fast to mention it, about all the matter. All the matter in the universe and all matter on Earth. Temperature, T, equals matter. And times that, one gets quantum entanglement. So temperature of matter, cold, makes a matter that gives darkness. Temperature of matter that is hot gives matter that gives light, suns, and so on. But that is all decided by quantum entanglement. And this shows you how quantum entanglement of all solid matter comes to be. It is all decided by temperature. So you're making any technology on Earth, this will help you understand it a lot more. Because the temperature in which you are making a piece of matter, steel or computer parts or airplanes or cars or anything, plastic, plants even, the temperature is what shapes matter, basically. They saw that completely wrong. They made up some Big Bang theory or something, you know. That's how matter is created, but how the universe was created, that's something, I mean, they say it blew up. First of all, there is no force to squeeze all the matter together for a Big Bang to happen, number one. Number two, if matter is squeezed, well, it blows up. All the hot matter would blow up before it's even squeezed. So the universe would then be just a cold, dark space, because if matter was squeezed to one point, like they say, the hot matter would have all blown up. Supernovas blow up are evidence of that. Suns blow up like that. But they say all the matter was in one point and then it went bang, and that's the Big Bang, you know. So they got the temperature part all wrong. But that's what they're missing, quantum entanglement right there, and dark matter to have the whole picture. But the Big Bang, I would say to people, that's just some dude who was bored, he didn't know what to do, he made some shit up. That's all the Big Bang is. So temperature equals matter, and one gets quantum entanglement. So what temperature you put into matter decides how it will become solid. And that can help people in making any piece of matter any piece of matter on Earth, plants, computers, anything. This equation can help people out to understand how to quantum entangle matter, which is a big part of it. So. And right here it says acceleration of all quantum entanglement equals mass. That's also important to know about all matter, but also how all matter in the universe is as well. For all, quantum entanglement is identical to mass, because the denser something is, the heavier and different it behaves and everything, and so on. So all quantum entanglement in the universe, to it, mass is identical. So if something is this big, quantum entangled to be a meter, then the mass behaves according to the atoms and how they are quantum entangled. If something is this big, entangled to be, then the mass is that size. So mass is always identical to the size of the matter, and the size of the matter is decided by how it is entangled to be together, with some exceptions of chemically entangled things, but there's not many of those. So. Okay. So this is now an equation that no, that's not the one. This one I can explain is an interesting one, an example of that, of a piece of matter with mass on Earth. This is nuclear, but it's about all matter. This is about all matter. This is just how microgravity gives mass to things on Earth, but the following equation is about all matter. But it's just to explain the uranium atom's mass to people, which is sort of like a big example of things. So speed squared, which is 1,675 kilometers per hour, that's through microgravity. So that's decided by distance from the gravitational center. How far away we are from the gravitational center, that's the speed one gets there. If he's closer, then it's less and less. If it's further away, the speed is more and more through microgravity. So proportional to that, one gets the speed squared, which is 542 meters per hour, which is acceleration of mass through nuclear matter. So there you have exactly, this was nuclear matter right here. That gives you the exact number when mass, gravitational pull of it, which is a mini gravitational pull, when mass comes into it, that's the speed on the equator of mass coming into matter. 542 meters per hour, which is acceleration of mass through nuclear matter, which is identical to the weight of the atom. So as that spherical mass comes into nuclear matter, it pushes on the atoms, so to speak. Just like gravitational pull pushes us down, in this quantum realm mass, they would call that the Higgs field, but that's just dumb. Like some explanation of something that makes no sense. It's all mass and space and gravity. So that gives, that acceleration of mass identically gives the weight through the atom. And then times that is the atom through density. Times that goes the fire of the atom through density. So the mass is going through the atom and through, sorry. Times that happens the fire of the atoms through density, which equals quantum entanglement, which equals 127 particles, which is uranium, the uranium atom. So that mass, when it squeezes matter, decides the fire of the atom, because the squeezing of mass, that like mini gravitational pull on matter, it decides how dense the neutrons are, therefore it decides the temperature and then how far the fire will go. That's just in nuclear equations. And that is identical to the weight of the nuclear atom. So that's the whole explanation, just to understand the exact quantum realm weight of the nuclear atom. So it's 542, and then one gets the exact number of the nuclear atom. Like when we are on a scale, but that is decided by the number of particles of it, 100 or 127. So they too, the size of the atom decides that weight as well. Just quickly thought to mention that. So this is one formula about all elements on Earth, more important in here, because it also explains on other planets masses and everything. So microgravity, but other planets have a similar microgravity, some different in speed and size, but the same sort of similar thing. Microgravity through acceleration, which equals 1,675 kilometers per hour. Proportional to that, one gets acceleration of 542 meters per hour, equals the speed of mass into the element, any element on Earth. And proportional to that is the weight through the atom. So when mass comes into any element, it gives weight to the atoms, and that weight of the atom. In nuclear physics, it's important because that gives the explosion and stuff, but it's about all elements on Earth. This part I just didn't see, but I didn't even write this one down. Yeah. Well, this one I didn't write down. So times the V, I don't remember what it is, of the atom through quantum entanglement equals density, times one gets the atom through quantum entanglement, which equals density, which equals the element, which equals the number of particles. So the more particles, the more weight. That's what it says through the atom. And that identically explains the weight of all atoms, of all elements on Earth. So the difference is where they are, how far away they are from the gravitational center, the center of Earth, and the size of them. And that decides the weight of all atoms in the quantum realm, basically. So that is an explanation of that, which is to understand the masses in the quantum realm and not the Higgs field. The Higgs field, like that's, oh, there's some imaginary field that gives mass to atoms. Everybody already knew that atoms have a mass. How do you think things blow up? What? Sunshine blows up? I mean, the Nobel Prize Committee, that's like really, sometimes they're even funny, like, oh, this dude discovered the field that gives mass to atoms. Well, what gave mass to atoms 10,000 years ago? What? The tooth fairy? Everybody knew that atoms have mass. We're all made of atoms. What? Oh, we have weight, you know, duh. They gave a guy a Nobel Prize for that. I couldn't believe that. Okay, so this is now about microgravity and mass. Just to explain it so that it's easily understood in a more simple explanation. So microgravity equals mass times the distance through space. So the further away we are from the sun, we are from the Earth, the more we'd weigh. Okay, that's why on satellites clocks tick differently. The distance through space, which equals incoming mass, the intensity of incoming mass. That's intensity of mass. So a clock on a satellite, mass squeezes it more than us here, and that's why it ticks differently. So it's that simple, not because of space-time or something like that. And that happens, and then one gets times speed through space. So the moon is also here. The moon's gravitational pull is also intensity of mass on it. It too is in microgravity. So it's part of microgravity's mass. So the same mass that gives mass to our atoms, that's the gravitational pull of the moon. But not weight. We get weight from the solar system mass. That's gravitational pull. But the mass in our atoms, that comes from microgravity. So microgravity equals mass times distance through space, which equals incoming mass times speed through space. So how fast we are going around Earth and how far away we are from it decides the intensity of mass on us and all clocks. So that's why satellites tick differently, just to fast explain that. That too is part of space. That's just space near us, but you can then imagine on other planets that it's quite similar, and people then understand the math and physics about it. So this is microgravity equals time, time, space through speed. So that you can say is about the clocks. So microgravity equals time, time, space through speed. So if you are further away from the Earth, then the ticking of the clock changes and so on. So distance from the Earth equals the intensity of mass on matter times space. Distance equals intensity of mass times space, which is identical to the measurement of time. And that exactly is an equation that explains why on satellites clocks tick differently, why they tick differently on airplanes. Scientists did that sometimes. They took an atomic clock that measures million parts of a second, and then they saw that the clock on the satellites and the clock on the airplane ticks differently. But that is simply understood not through some space-time, that's simply decided by the distance from the gravitational center of Earth. And this gives people understanding of time anywhere in the galaxy. Any planet in the future somebody's on, he will know the exact gravity time, how gravity designs the software of time. And then he'll have an exact measurement of time anywhere in the galaxy, so through the correct math and everything. But basically speaking, time doesn't even exist, you know. Time is an idea, that's just gravity and mass, so and that's what they're doing. So okay, did that. This is, yeah. Okay, I can mention this equation quickly. So the gravitational center through distance, it gives identically to it intensity of mass divided by matter. So the intensity of mass is on matter times space. So if it's further away, the distance is different, then there is more intensity of mass, simply put, and that equals time divided by gravity, through gravity. So that's what decides time and the ticking of clocks and everything. So this also explains that, the same thing. Okay, so this is now the part about Einstein. Yeah, Einstein said E equals mc squared. And it is part about space too. Einstein first wrote mass equals energy divided by c squared. And then he later wrote E equals mc squared and everything. I did a lot of research. I started studying Einstein like 10 years ago when I started writing in physics and everything. And I thought Einstein is the smartest guy around, you know. But 10 years later, then things changed, of course. But I mentioned him in the books a lot. Einstein did have genius ideas, of course, but not all of them were that genius. So some mistakes he made. So okay, so there it is. This is now my explanation of that, of Einstein's equation E equals mc squared, but this also helps about understanding the universe and everything. So I would use Einstein's equation to more correctly explain it, and I would say mass equals c squared divided by energy. Because mass and c squared, that's the equations I mentioned earlier, similar to it. Mass equals outgoing mass. C squared is the speed of light. Outgoing mass is what moves light. So it decides the speed of light, but it is also decided by the size of the photon. So mass equals the speed of light divided by energy. because this speed of light is millions of times faster, but when a photon comes into it, you get the speed of light. So mass equals c squared divided by energy is what I would say. But this speaks about energy when it leaves the sun, not energy in matter. In matter, also in matter, the hot energy, which is c squared in most cases, is never equal. It is a lot less and so on. So here are some equations that explain that. People like a lot, E equals mc squared. And so this is how I, in the end, explained it, to attempt to explain it more thoroughly and more correctly and everything. So mass equals c squared, because they are the same thing. Mass comes in as gravitational pull and comes out as quantum gravity outgoing mass and moves light. So, and that's what moves light. Therefore, that's what c squared actually is, the speed of light. But of course, the photon itself too decides the speed of light and is a big part of it. So mass equals c squared, which is divided by energy, which equals the size of the particle through temperature. The speed of light in c squared, in the great beautiful explanation of things, happens because of temperature. Temperature is a highly complex thing to understand in physics. There is temperature in space, there is temperature in matter, there is a big temperature, there is quantum realm temperature, which is very different. See, inside a neutron, its own energy decides its temperature. The outside temperature, neutrons don't really care much about it, unless they are quantum entangled into big pieces of matter, and then the temperature is coming out of them. So the quantum realm energy of a neutron and temperature decides all the big temperatures in our big realm. So the quantum realm, the energy of a neutron, and all of them, let's say on Earth, decides the temperature on Earth, so to speak. All of them of Earth. So the quantum realm decides the temperature we are in, basically. So that would be an explanation of that. Mass equals c squared, which is the speed of light, divided by energy, which equals the size of the particle. The speed of the energy is decided by the size of the particle through temperature. But this is just to explain it through E equals mc squared. So mass equals the speed of light divided by energy, which equals the size of the particle through temperature. But temperature as well, in almost all matter, decides that size of the particle. The sun is hot, so it gives light. So it makes photons. The temperature of the sun makes photons and gives them the speed of light. So temperature decides the speed of light. And in my equations, some of the most beautiful and simple ones are mass equals temperature. That is like a way forward, a very beautiful way to understand things. So, and to simplify it, mass equals c squared divided by energy, which equals the size of the particle through temperature. So matter's quantum realm, neutron and proton temperature decides the size of the particle, and that gives energy, and that gives the c squared. And it all happens because mass makes it turn into energy in the first place. So that's just to simplify that. And to nicely understand E equals mc squared properly and correctly, you know, down to the quantum realm details. It is even very beautiful. Of course, billions of people love E equals mc squared around the world. And then to continue, sometimes in my work, when I was younger and everything, I thought like most people, Einstein, Newton, I know almost the whole life of Einstein. Studied it for years, even had 4 wives, he was a patent clerk. But even Einstein did his best work when he was a nobody. That's something in psychology interesting. Newton did his best work when he was a nobody. But when they became famous and everything, it's like they changed, so to speak. And they sort of left physics and went more into human psychology realm. You know, they're famous, everybody likes them and so on. So that sort of, from my point of view, affected them to not be so good in physics afterward. I mean, no offense, you know, to them, of course, but that sort of study of psychology and everything. So that's like a beautiful, easy way to understand in detail E equals mc squared and that. So here quickly I would add two more equations that are just in other places written, just so people more further understand this. Temperature equals mass times c squared. It can also be told like that, very beautiful and great to understand, because temperature decides c squared and mass decides c squared. Energy is just what comes out of matter. Matter is just sitting there, but temperature and mass make energy, basically. Those are the two main ingredients, and the energy is what somebody gets out. So one beautiful equation is temperature equals mass times c squared, or times the speed of darkness, and so on and so on. Another nice equation to just say is mass equals temperature, which equals outgoing mass, the force that moves all energies, divided by energy through temperature, which equals c squared through the size of the particle. Because c squared is decided by many things. Number one, the size of the photon, which is made by temperature, and c squared is also decided by mass, because it turns into outgoing mass and moves the photons. So that's to more thorough understand to explain that. Before, I loved writing these equations in earlier books when I was doing it. There's tons about Newton and Einstein and everything. So there is that equation, mass equals temperature, which equals outgoing mass. That's the force that moves light. And outgoing mass is divided by energy through temperature, which equals c squared through the size of particle. Now the big explanation here is, let's say in the galaxies and suns. Suns have hot temperature, their outgoing mass carries energy through temperature is very, very important. And I explained that before with nuclear explosions. As soon as the heat stops, it turns into smoke and it's gone. There's no more photons coming out. So it's like that with photons, even in the galaxy, even when energy goes far away into cold space. When energy of the sun, light, leaves the hot temperature, then it cannot anymore exist. Because one individual photon, and they are very spread apart when they leave the solar system, it can't exist in cold space. So that would be like an explanation of that through evidence and everything. Okay, so interesting about Einstein is, you know, he told people E equals mc squared, and that's what people in general will hear about that, read the theory of relativity. But the Manhattan Project, they made a nuclear bomb through sort of like that. So that means they knew more about E equals mc squared like 100 times more than Einstein. Just their work is secret, you know, but that means they were smarter like a lot than Einstein and so on. But maybe in secret, Einstein even helped out in that work. Maybe that was just held the secret and so on. Perhaps, so. But nuclear physicists, you know, that was secret back in the old days with the Manhattan Project and everything. But evidence then shows they knew about that a lot more than even E equals mc squared and everything. So, and Einstein, that's like one thing, you know, well, okay, you know, many people in physics, they see some things they say to the public, you know, people on top and everything and so on, even Microsoft, even Big Macs, you know, McDonald's, they sell us the sauces, the hamburgers, but nobody tells you how to make it, of course. So Kentucky Fried Chicken, even that is secret, you know, the recipe and everything, Coca-Cola and so on. So, you know, to the general public, to us, they say very, very little. Oh, E equals mc squared. Oh yeah, thanks, man. Does that mean that the light comes out of the sun? Well, okay. So yeah, but this physics now people will understand even more than even nuclear physicists and everything. This is like a revolution, great in understanding the whole universe and the galaxy, what it is about. So here now, this is dark energy. This is dark energy, and to explain it, dark energy is very beautiful and everything, and here it says new understanding of Star Trek, even going to other galaxies, because dark energy reaches other galaxies. That means on it we could even go to other galaxies. Of course, nobody will believe that, but there's a real physics about it. So, so the equation begins. Dark energy equals acceleration of mass, which is divided by, in the space of dark energy, the acceleration of mass is divided by the gravitational center of the galaxy, which is the black hole, times the force of outgoing mass, which is behaves like an energy. That's why they call that even dark energy, because they see how it behaves. It behaves like energy. But the astrophysicists, but they had no clue what it is. It's invisible and so on, or how it's made, how it comes to be, and so on. And this is, so it is a form times the form of outgoing mass that comes out of a black hole, which is alike to energy. See, when gravitational waves come out of a black hole, a small one, then that's gravity waves, and it's just like some shock waves coming out. But when it comes out of a center of a galaxy, because that's a lot bigger black hole, then it's dark energy. So, to simply understand it. And that equals the expansion of space, as people would call it. Space is not really expanding, and space is fixed. How big space is, it is. Just nobody knows how big it is anyway. But the galaxies are just moving, you know. So the scientists are thinking, the astrophysicists, that space is expanding. Space is not expanding, just the galaxies in it are moving, that's all. So that's to quickly explain that. That's the text and everything, and further explanations of that. So the speed of movement of dark energy is divided by incoming mass, which equals the center of the galaxy, which is the big black hole. And equal to that, one gets the intensity of outgoing mass. The intensity of outgoing mass in the in the gravity of the galaxy. Now we gotta see what is. Yeah, okay, so the intensity of outgoing mass goes through the gravity of the galaxy. That gives mass to the sun. It comes into the sun's gravitational pull, comes out as sunlight, and then hits us. So through this understanding, people understand sunlight in part is dark energy too. Then sunlight hits us and does that. Times a sphere divided by acceleration. So dark energy and the force coming out of the central black hole is a sphere. People, we always assume like that gravity is a disk, that the galaxy, sorry, is a disk. And the stars do take shapes in most galaxies as far like disks. But the force itself of gravity of the galaxy and the outgoing mass, which is dark energy, is always a sphere, which is divided by acceleration, and that equals the expansion of space. Because that sphere of acceleration of dark energy and its speed, it hits the nearby galaxy. That I explained earlier. It hits the nearby galaxies and then makes them go away from each other. But like to explain it simply, that's sort of like bumpers, so that galaxies don't slam into each other and be destroyed. So they have bumpers, forces that make them go away. And the galaxies are moving, and to telescopes it does appear as if the space is blowing up and expanding, but where it is expanding, what into, and how big it is, that's unseeable, so nobody even knows that. I once thought that all the galaxies are going in a circle, but the big, huge understanding here is the center of galaxy, which is the black hole. Dark energy is coming out of it. It's a sphere and it hits all the other galaxies, and then they have an effect on each other's movement. But then the big question is, where does the incoming mass of the center of the galaxy come from? And that's a whole new force that nobody knows that even exists. But sometimes I ask myself, you know, how big could the universe be? Well, then that's an even bigger mass that gives mass to the center of the galaxy. And it's moving. So dark energy affects how a galaxy is moving. And then that affects the incoming mass of the central black hole of a galaxy. But that shows then that indicates, it's pointing towards that there is even a bigger mass that even dark energy is. Even a bigger mass than that moves galaxies, that there is even a bigger mass, because once one understands that dark energy is just outgoing mass of the center of the galaxy, then one would ask the question, then where does the incoming mass come from? And that's like, that sort of indicates that there are even bigger masses out there that feed the center of a galaxy, and it turns into dark energy. But where does that come from? What that mass is totally unknown. But that sort of shows that the universe could be a lot bigger than that we even know. But to explain mass simply in the universe, we feel gravitational pull. Our atoms feel microgravity. But let's say the gravity of the galaxy and its mass, we don't even feel it. It doesn't even affect us because we are too small for it. The gravity of the galaxy gives mass to suns and moves suns. Planets, moons, people, it doesn't even care about, so to speak. It doesn't even have an effect on them, or it doesn't even move them. It moves the whole solar system, but it doesn't give us mass, basically. That's what I'm trying to say. Yes, it does move us. The gravity of the galaxy moves the whole solar system and us in it, but it does not give us mass. And there people can understand why we need something so solid and heavy as solid electricity. Because solid electricity would be so dense and strong that the gravity of the galaxy would see it as if it's a part of a sun even. And it would tap into that huge mass of the gravity of the galaxy, and that in part gives us then Star Trek and so on. And this is also about dark energy, a simpler equation to explain that. The force, which is dark energy, equals speed squared through space times distance. So dark energy increases speed with distance. But the distance here is between galaxies. So when dark energy gives mass to suns, comes out of a black hole that's center of galaxy, goes through suns, it goes at one speed. But once it leaves the gravity of the galaxy and is in between galaxy space, then it even increases speed and goes faster. So to understand it with mathematically correct, the force, which equals dark energy, equals speed squared through space times distance. Distance here means between galaxies, that distance. So that's the distance it mentions here. And here are just some simple equations of that. Dark energy, the force equals dark energy, which equals space through speed squared, and divided by that speed and space, one gets the expansion of space and everything. So, and that would be about dark energy, but later in the video I'll explain it like a whole galaxy and the whole universe, how it works and so on. So another equation that simply just explains, quick one, of dark energy would be dark energy equals acceleration of a force through energy. So dark energy works like energy. How sunlight comes out of a sun, that's how dark energy moves and behaves. Just the speed of it is different and everything. Times speed squared divided by space times distance, it equals incoming mass times incoming mass into gravity of the galaxy divided by acceleration, and times one gets the expansion of space. Okay, so now this is Newton. To return to gravity and how it works in space and everything, this is now through Newton's views of things. So Newton said the force equals gravity times mass divided by distance. But to properly and mathematically correctly understand that, I changed even how I wrote another equation similar, how I would explain it. And in my books it says, in further books, this is an earlier one, so it would say force equals gravity times mass divided by mass times distance. Because the force of gravity, let's say it's a sun, gravity is coming out of it, and it has mass. And then the mass of the sun divides into the mass of planet Earth times distance. So if we were further away from the sun, we would get a lot more of its mass, because we would go through a lot more space, therefore we'd get a lot more mass that's coming out of the neutronium core of the sun. So the force of gravity, I could not find those equations are in other books. So the force of gravity equals mass divided by mass times distance is the mathematically correct, really correct explanation of things. Is how I would explain that. And there is now equation. So, but these are some earlier, because this is book number 4, I have a book number 5, but that will come in later shows, even about space and everything, more equations. These are some equations I thought to cover it quickly and in short, but about space I have like hundreds of equations. Some better, some longer, and so on. About supernovas I have like ones that big, just to explain one supernova. So the force of gravity, this is my equation now, equals distance times the space of mass sphere. So just like gravity that comes out of a sun, planets are there, is a sphere, and so is mass coming out of it. But mass goes a lot further than the gravity. And that divides into space, that divides into movement, into movement squared, and equal to that is intensity of gravitational pull times speed squared. So that says the gravitational pull of all planets, moons, and suns, and so on. Their movement equal to it, how much matter is moving, that's how much intensity of gravitational pull there is on a sun, moon, planet, and so on. A sun does have sort of like an atmosphere, but a lot of matter is still coming out of it. There, the photons are very, very thick in plasmas, and then gravity sort of sees that as gravitational pull, even above the sun a little bit. So intensity of gravitational pull, that's how fast someone falls when he jumps out of an airplane with a parachute and so on. 9.8 seconds it's on Earth. The movement equals intensity of gravitational pull, which is the speed of gravitational pull, times speed squared. So how fast a planet is moving, that also decides that. So here is another equation about time. Because time is like a part of gravity and part of space and everything, and it is important. There is a form of understanding time and a different one in every part of the galaxy, everywhere. But time is part of gravity and mass, of course. They give the measure of the clock. They decide it. So clock is just to me, a clock is a lot more important to measure mass and gravity than time. Time is just something that to me tells the gravity and mass. So the intensity of mass sphered, it's always a sphere, equals the measure through a clock times speed squared. So if the clock was moving faster, then the measure of time would be different, of course. Einstein said that if one moved at the speed of light, then the ticking of a clock would stop. Everybody knows that probably from Einstein's stories. That's what Einstein said. But why would he think that or say that? That just means that at the speed of light, mass would be squeezing the clock so much that no ticking would be, because it cannot tick then, because mass is squeezing it so much coming into it spherically that it cannot move the dials of the clock as they tick. Mass would squeeze it and it cannot move. So Einstein explained that like that. If you go at the speed of light, then there would be no ticking of the clock. But that was in Einstein's time. Now we have electric clocks and atomic clocks even. But even on them at the speed of light, electrons would work fine, but the atomic clock would have trouble to work probably at the speed of light. But an electric clock probably would work even then. So that's just simple to explain time. Time, gravity, and mass make the ticking of clocks. To simply explain it, intensity of mass sphered equals the measure through a clock times speed. So where the clock is in gravity and how fast it's moving through space of mass, that decides the incoming mass into it, and that decides the ticking of a clock. So another equation to explain that: the clock divided by measurement equals intensity of mass sphered. So how mass comes into a clock affects how it ticks. Is it fast mass or slow mass? Like gravitational pull comes into Earth, that's how mass comes into a clock. So just in microgravity, in our clocks, microgravity mass comes into them spherically and then affects their ticking. On satellites and on Earth and on an airplane, atomic clocks and everything, especially atomic clocks, because atomic clocks, the mass in microgravity affects the atoms and so on. Except the electrons, because electrons are moving at the speed of light, so they can reach some masses that are even maybe bigger than microgravity. But on Earth, all atoms get mass in microgravity. So the measurement of a clock equals the intensity of mass sphered, that comes from microgravity, times gravity divided by speed of movement squared through the space of mass sphered. So where the clock is in the space of mass sphered decides how fast gravity is moving it through that space, and that affects the clock. Then that gives the incoming mass into a clock, and that affects how it's ticking, basically, to simply explain it. Because a clock has internal parts. The atomic clock has atoms. And then mass, how heavy those atoms are in mass, that affects how the clock ticks. Even the electrons. Mass comes into them, they are heavier a little tiny bit, and then a few milliseconds, some clocks don't work properly and so on. So the clock divided by measurement equals intensity of mass sphered. So how mass is coming into it times the speed of movement squared, which is identical to microgravity. So clocks on a satellite, on an airplane, on Earth are all in mass of microgravity, and how distant they are from the center of mass decides incoming mass into them, because that determines their speed through the field of mass, because the further away they are, the faster they are moving around Earth, and then that gives different measurements on clocks. And then people understand, Einstein had some ideas, but space-time, to me, that was totally wrong. Einstein called, okay, he didn't know these things, but he would explain that space-time, space and time. So then you lose gravity, you lose mass. The two most important things in all the forces in the universe, as far as physics, you lose that, you call it some space-time. That's like for little children explanation or something. To me, I mean. Space-time, so what? Where you are in space decides what time it is. Like, that's totally like, you know, for little kids stories, you know. But to properly understand it correctly through physics, how mass comes into a clock decides how it ticks. All clocks, electric, atomic clocks, and ordinary clocks. So, and what's beautiful there, I even designed a clock that measures mass anywhere in the solar system and the speed of gravity. So you would just need a clock, and you have an exact measurement of speed of incoming mass and speed of rotation around the sun and everything, or around the planet and so on. Very beautiful, and one could make it for like $100 because it's just a clock. So a beautiful patent. That will be explained, that patent, of course, in future shows and everything. Okay, so I got to the main equation. Very beautiful equation to me about gravity itself. All divisions of mass inside gravity. So from sun to the planet, from the planet to the moon, from the center of galaxy to the sun, and so on. A beautiful, but sort of like Newton's, through Newton's view, but changed equation that explains all of that. And the force of gravity, that's like Newton's, the beginning. The force that is gravity, that equals gravity, equals the division, equals mass divided by mass times distance. Newton said it is mass times mass divided by distance. But I saw that later in work and through evidence that it's incorrect. So force equals gravity equals mass divided by mass times distance is what I put. This equals doesn't have to be there, but that's simply to explain. So mass, let's say of the sun, becomes the mass of the earth. So mass of the sun is divided by the mass of the, divides into the mass of the earth times distance. So if we were more distant from the sun, we would get a lot more mass, and it would pull on us a lot more, the gravitational pull then and everything. So that's a simple equation to explain the division of mass inside gravity about the whole universe. It is in detail later explained. So there it is. The force that is gravity is mass divides into the mass of the sun divides into the mass of the earth times the distance between them. So the gravitational pull and mass of the earth is decided precisely by the distance between earth and the sun. So if we were further away from the sun or closer to the sun, we would have more gravitational pull on us. Because planets closer to the sun, they have more gravitational pull because they move faster around the sun, but they are smaller. But the planets further away from the sun go through a lot more mass, through a lot more space, therefore they have higher gravitational pull intensity. I mean, astrophysicists, they watch, let's say, comets when they hit Jupiter, they observe that and everything, and through that they sort of observe how that goes on. But Jupiter is a gas giant. The comet goes under, and that's, but later they see the explosion, I think, because comets then blow up and everything. But Jupiter again is a gas, so a comet is going through dense stuff and everything. That's also some math and everything. But this is a lot of equations, but people can see it is complex. It's not easy to understand just our solar system, let alone the galaxy. A lot of math, a lot of equations and everything. So later it would go on, the force equals gravity, which equals mass divided by mass times speed squared through distance from the gravitational center. Just to quickly explain those further equations, this is the same one, and now it goes into math. This is through math, the explanations of it. So the mass of the force equals gravity, which equals mass of the sun, which is 2.0 times 10 to the 30 kilograms, is divides into mass of the earth, which is 5.78 times 10 to the 24 kilograms. And that equals the mass, which is 34602-7612 kilograms, times the distance, which is 1.5 times 10 to the 11 meters. It equals then 519031419 times 10 to the 11 meters per that's the mass through distance, which equals the meters. But this is just an equation to explain how mass moves between. I would have to see what that exactly, I have millions of equations, so I can't really memorize all of them. That's why, many times, that's why I even write things down and everything. Yeah, that's it. So this is an equation people will not understand, but this is an attempt to show when mass is moving from the sun to the earth, so as it is moving through 1 meter, how much mass there is, which is a totally unknown, invisible place, which is the movement of mass through gravitational space before it hits matter. When it hits matter, then we know what it does. It's a gravitational pull, this and that. But as it is moving from the center of mass, which is the sun, between the sun and the earth, so this is an equation, an attempt to explain that. A little bit more complex, but and those are all the explanations, tons of things, which would take very long to explain and everything. So this is a simple explanation. So the mass of the sun, force equals gravity, which is mass of the sun, 2.0 times 10 to the 30 kilogram, divides into the mass of the earth, which is 5.78 times 10 to the 24th kilograms, times the distance, which is 1.5 times 10 to the 11 meters. So this distance decides this mass, mathematically exactly. It decides why this mass becomes that. This is how many kilograms Earth has, and that's precisely how much gravitational pull and mass there is, and mass makes those kilograms. But that's also about the size of the Earth. But the mass is decided by the speed at which gravitational pull comes into Earth. So if we were, let's say, further away from the sun, then this number would be a lot bigger. It would be a lot more mass, and Earth would probably be even smaller because mass would be squeezing it a lot more and things. So then there are many, many equations about this. This would be like a simple, fast explanation of that. The force equals gravity, which equals incoming mass, which equals outgoing mass through gravitational pull divided by weight times the speed of matter squared through the space of mass, which is divided by distance. So again, how far away we are from the sun, it is divided by distance and everything. These are not, but people can observe as I'm explaining the equations, I'm trying to do it fast. If I want every detail in the text, although it's there, it can be translated if somebody likes to. But if I went to the details, it would be like a show that's like 20 hours or something. And it is a fast attempt to explain the mass of the galaxy and everything. Okay, this is again about the sun and the Earth, which I just explained. And this one as well. Okay, so this is now highly complex. A highly complex movement of mass from its center of galaxy all the way to Earth, and it is a very, very complex one. Just see what there is. Yeah, mass divides into mass times distance is actually a formula about all the matter in the universe, which is inside the gravity, of course. It explains the gravitational pull of all matter in gravities, all of them, therefore. And one can take this math, an equation that I just explained, and he can know the weight and the mass and the gravitational pull of all the matter in the universe, along with other formulas that are about matter inside the gravity of the galaxies and bigger galaxies as well. So that was the attempt of the whole text and everything. So this is now about the transfer of mass. So the force equals gravity, which equals transfer of mass, and that's an equation how mass goes all the way to Earth. So it begins the mass of the center of the galaxy, and that is a speed of 2,160,000 kilometers per hour through dark energy, which divides into outgoing mass of the gravity of the galaxy, which is a circumference of 100,000 light years, and times the distance, 38.500 light years, which is 77% of the gravity of the galaxy. It equals the mass of the sun. So that's the distance between the center of galaxy to the sun, and that equals, then that distance decides the mass of the sun, which is the 2.0 times 10 to the 30 kilograms divided by the circumference, that is how big the sun is 60877 times 10 to the 12 kilograms. That's the weight of the sun. And then that happens through the speed, according to astrophysics and modern astrologist, with 750 kilometers per hour, 750,000 kilometers per hour through gravitational space. Now, I observe gravity as one space, mass as another space, and the distance measurement is where you get the exact mass. In gravity, all suns move 750,000 kilometers per hour according to astrophysics. So that speed in my physics divides into a precise measurement of mass through distance, the exact number. And I got 6 million kilometers per hour through the space of mass is how fast the sun moves in the galaxy. That's through my physics. That's astrophysics, modern science. That's through my physics, because I measured the distance of the sun from the center of the galaxy. But they just would say that all the suns are moving the same speed. And they're moving 750 kilometers per hour, they would say, through gravitational space. But gravitational space has a lot of different distances, you know. So if one sun moves through 100 million kilometers in an hour, and another one moves 10 kilometers in an hour. If one sun moves 10 million kilometers in an hour, and another one moves 100 million kilometers in an hour, then in an hour this one went a lot faster, the one that went through 100 million. That's the whole point of understanding the mass of all suns in the galaxy. But astrophysicists would say, oh, they're all going the same speed and that's it. You know, so then one identically equal to that mass of the sun gets outgoing mass of the sun, which is, no, that's not that. Gotta see what that really is. That's all there, all there. Oh yeah, that is that. Just this is the measurement of it. So identical to 6 million kilometers per hour through the space of mass is the gravitational pull of the sun. Then through that speed, the sun gets its gravitational pull, and identically equal to that is outgoing mass, the force, which is the same as the incoming force, which is 2.8 times 10 to the 30 kilograms, which divides into the gravity of the solar system. Then that gives mass, the gravity of the solar system gives mass to us, and that's our gravitational pull and gives us weight then. And that is equal to distance 82 astronomical units through a sphere, times the distance, which is 1.5 times 10 to the 11 meters. It equals mass of the Earth then, which is 5.78 times 10 to the 24 kilograms, the circumference of 510 million and 100,000 kilometers squared, through the speed, which is 108,000 kilometers per hour. So through that speed, we get the mass of the Earth and everything, which is gravitational pull and everything. So that explains, this is a little bit more complex because of the math and everything, but it explains the transfer of mass. So it starts with the mass of the center of galaxy, it goes into the sun, and then it becomes the mass of the Earth. So in my physics, all the masses are one mass, but they just go from one thing to another and they switch. But like this, the mass of the center of galaxy, the black hole, gives mass to billions of suns, and then them to 10, 20 planets. Dwarf planets could be hundreds of them. So, and then people understand in a whole galaxy how that really goes and everything through transfer of mass and understanding it. And then when people understand transfer of mass through the galaxy, that is the physics that points towards Star Trek. And then all we gotta do is tap into the mass of the galaxy, for which one needs something as dense as a neutron star and everything, or even denser. And then we got Star Trek, which is the big explanation on dark energy, because the mass coming out of the gravity of the central black hole, that is dark energy, basically. And that speed that I mentioned there is also the what sometimes causes supernovas. Our sun is 6 million kilometers, but when it reaches 10 million kilometers in the field of mass, 12 million kilometers, well, then that's supernova, so to speak, territory and so on. But even slower suns sometimes blow up, and smaller ones and so on. But the big thing about the sun is the suns are some very, very big. And then even how fast its mass is, in the center of it, in the neutron core, it is a lot denser and heavier, because all that mass condenses into one space. So this is now a simple way to see that quick explanation. The speed of the sun, which is 6 million kilometers per hour through the field of mass, which is important, not in time, not in gravity, but in the actual measurement of space, which is the field of mass. But so how fast it is moving through mass is 6 million kilometers per hour. In gravity, they're all moving the same speed. That is correct. But through space, they're all moving at different speeds. So, because space has different measurements, of course. Some space is smaller, some is a lot bigger. The end of the galaxy circle around galaxy is a lot bigger than the one near the black hole. So that divided by 3,085, one gets the exact measurement of the gravitational pull of the sun, which in my physics is 1.944 thousand kilometers per hour /8. So 1,944 kilometers per hour is the speed I got. That's how fast mass comes into the sun. But as mass in the sun gets closer and closer to the circle, it is all a sphere. So there it gets denser and denser and denser, therefore stronger and stronger and stronger. That's understandable as well. Which is called, in my physics, it is called the density of mass. So that is also very important when it's in galaxies and everything. So now these are just equations that further explain that and everything. Then how light comes from the sun and everything, and the energy, the speed of light is right there and so on. So those are just further than detailed explanations about the details. But people can see that these equations in books, it is all about detail. I even measured, that will be in other shows about suns and supernovas and how suns work. A whole show will be on that. And I even have measurements about when sunlight moves, so how much the quantum realm distance is between the photons. And then the further the sunlight goes, those quantum distances increase and so on. So in physics, that's very important. This is now easy and simple. It's about the density of skin. People go bald because their skin is too thin and so on. Women's heads are genetically designed to make thick skin, but ours aren't, and that's why men go bald and so on. So that's the explanation of gravity. This is one that I thought was the most beautiful to point out from this book, which is the force equals gravity times mass divides into mass times distance. Not divided by distance like Newton said. But Newton saw that through mathematics. This is physics from observing reality, so to speak, which gives you facts, details. Newton, of course, Newton was genius and everything, but Newton sort of saw it through math. He thought to say that it's divided by distance, but and it's not mass times mass. So he was just he was sort of looking at through math and mathematics there. Newton's laws are geniusly correct, but that was because he saw that through evidence, through reality. But the other equation that I mentioned just of Newton, he saw that through math and thinking, but Newton didn't have, you know, they didn't have the Discovery Channel, they didn't have YouTube and shows about galaxies and how they work and everything, how they move and everything. They didn't have that much knowledge back then. So Newton had no choice. He had to go into math and try to figure it out from that point of view. But the precisely correct explanation about that would be the equation that I explained earlier. So the force equals gravity, which equals mass times mass divided by mass times distance. That is like for all division of mass inside the gravitational spaces and everything. So this is one equation I just thought to show, which will be in future shows and everything. This is the entangled hydrogen right there. Thermoliquid hydrogen molecules. So thousands of hydrogen made together to create a rocket fuel about going to space and everything. So this was just one of the equations that explains that and everything. Which is also very important is incoming mass into it and the speed and so on. So, but it has many equations and explanations how to make that and everything. So that's thermoliquid hydrogen molecules to make a rocket fuel to go to the solar system and everything. Although antimatter is of course a better idea. And this is another equation that explains that. So this is like going through the solar system, so through gravity, through mass, but one example of a propulsion that can give us. So this is like a propulsion when we reach supernova shockwaves. So that's one explanation. That will be in future shows, like about the propulsions and go to space and everything. So the shockwave coming out it can reach speeds of 108 million kilometers per hour squared through a sphere, which is the explosion and everything of the fuel. Once thousands of hydrogen are entangled to form one liquid fuel, a big molecule and so on. And there it mentions the intensity of mass on the fuel, which would be at this certain speed, which is 8 million kilometers per hour speed squared. The intensity of mass, the math says, is 2,561 kilometers per hour squared. So that's the incoming mass on the fuel. And then that divides into weight. That happens through a sphere squared, and that happens through, that then has an effect on the weight through the neutrons, which gives the extremely hot temperature through the density of neutron, which gives the relationship of energies amongst themselves, and then supposed to give a great big shockwave explosions. And this is very interesting, like to point out, to go to the solar system and everything. Antimatter can get us to Jupiter like very, very fast, a few grams of it. But this would be a whole big molecule of thousands of hydrogen atoms entangled to each other through magnetic fields, they're ionized, and extremely cold temperatures and so on. So just few equations to show in future shows what will also be propulsions and technologies, billionaire technologies and everything, how to go to space and everything. So that's the equations and everything, and people can now understand how that all applies to observing a galaxy and everything. Like this is a whole galaxy right there, not seen very nicely. So this would be the end where all the faraway stars are, and that's the center right there. So by my calculations, and some evidence says that most supernovas happen right here, where at the end of the galaxy. And that's where the highest equivalent of mass is, at the end. So these stars right here at the end of the galaxy. The ones there have a lot less mass near the black hole and everything. And my calculations tell me that's where the most supernovas should happen. This is from the Hubble telescope, so computer program that shows real galaxies and everything. So to get back to that. So there it is. So that's the center of galaxy. It glows because there the suns are so densely packed. There are tons of them around each other very closely, so there it glows. But here they're spread apart. There's a lot more space and everything. And this is where the highest equivalent of mass is in suns, at the end of the gravitational field of a galaxy and everything. And I mentioned dark energy, dark matter, and now people can understand how that is very important in physics. Most scientists say, we have no clue what it is. You ask sometimes scientists about what is darkness? Well, darkness is nothing. But darkness, actually, it is the energy that we need to stay young and everything, like I explained earlier. There is one formula that explains dark energy equals mass times the speed of darkness squared, which is 550 kilometers per second. And that is the rate at which our atoms of skin and body are wasting energy. The cold energy, but we are cold matter, so we spend cold energy. The hot energy, we never glow, so stays in the atoms. So the cold energy spends away through the years of life, and the hot energy remains, like I explained earlier. And when the hot energy just remains in skin, then it's all old and hanging, because it's too hot in the quantum realm of the atoms. The important thing in the quantum realm is that the temperature of the neutrons and energy of the neutrons decides how matter functions and everything in biology and everything. So that's a huge equation about that. Dark energy, I mean darkness in a sense. So dark energy in space is something different. So darkness equals mass times the speed, 540 kilometers per second. So when our neutrons are too hot, that's all, then people die. The organs, that happens in them too. If the organs are too, then neutrons that are too hot. Because the incoming mass, like I explained about space, we too have incoming mass. It joins through the quantum entanglement of atoms and comes out as outgoing mass. And that's our shadow. So when we have a shadow, that's darkness coming out of us, which is an energy, our energy, darkness. I mean, of the human body. And it moves 550 kilometers per second, darkness, the speed of darkness. And that's the speed at which our atoms lose energy. So that math too helps in that physics and everything. And that's why all we have to do is refill our body with dark energy through food and through the creams and everything. And then that energy is filled again and we are young again. So it's real physics I'm trying to explain. It's not, but people by now probably realize through evidence for themselves and everything. So, so to go through the galaxy, there is the black hole. And the mass is coming out of it, like I explained through the equations. So, and that mass, which is dark energy, outgoing mass of a black hole center, goes into all the stars and gives them gravitational pull. So, if we want to make Star Trek, of course we do, then we need a solid piece of matter, even more solid than a neutron star, because in some sense there are some stars in the galaxy. There are magnetar stars, there are white dwarfs, there are neutron stars, but they're as big as moons. See, now the moon, our moon, the galaxy's mass and the galaxy's gravity don't detect it at all, not even a planet. But a magnetar star, it does detect, even if it's as small as a moon, so to speak. Some are smaller, maybe 15 kilometers. But because it is so densely packed with neutrons, the galaxy detects it as its piece of matter and moves it as a sun. Doesn't matter how small it is. So then people can understand, when we make solid electricity, it will immediately tap into the mass of the galaxy. And that gives power shock waves that are nothing before seen, even in the whole solar system. And a solid piece of electricity can do that. I have studied that for 5 years and everything, even more. Solid electricity and how to turn it into Star Trek and everything. And these are, what I'm saying are things that I have studied for like years and years. Did a lot of research, evidence, a lot of things. So in the end, I'm explaining the physics and everything. So when we have a core of electricity, the galaxy's gravity will detect it as a part of the galaxy, not the solar system. And that means it will have mass that is a million times stronger than our mass. Let's say a nuclear explosion, when it explodes, that's mass from microgravity. So that's like only the moon has lesser gravity. Then it's planets, then it's suns, and then it's the galaxy. So when we have a solid piece of electricity, it will give us to tap into the galaxy's masses, which is dark energy, and then we can go all over the galaxy through those big masses and shock waves. But there a person can see how we have dark energy, dark matter. Scientists sort of a little bit saw evidence that it exists, but they had no clue what it is. But dark matter can give us to live for thousands of years when we scientifically and correctly understand all of it, which is darkness and dark cold matter in space and on Earth. Graphene is just 100% dark matter piece of matter. So one would explain it. Of course, dark matter in space is a lot heavier and a lot denser, densely packed atoms, because they have passed through black holes and so on. But it is the same thing, dark, cold matter, that is darkness. That darkness comes out of it as an energy because of its temperature, density, and so on. So it is the same thing as graphene, basically speaking. Dark matter in space is like graphene, if you like. Because when a piece of matter passes through a black hole, all the energy that's hot would explode and blow up and disappear and everything, or it would evaporate into energy, radiation, light or something. But when things go inside a black hole, people don't see what happens and so on. But when a planet falls into a black hole, all the dark matter, it cannot explode. So a different version of events happens with cold, dark matter in a black hole than hot matter that just blows up and that's it. And so the evidence is pointing to all those things. So dark matter in space is simply just dark matter, graphene. When you pick up graphene, well, that's dark matter basically. Just the density and how it entangles is different. In graphene, let's say, it's 200 times stronger than steel. But that is simply because it's quantum entanglement, how graphene is entangled to each other. When it's not, when it's broken apart, then it's different. If one turns graphene into something else, then the quantum entanglement changes, and then that strength also changes and everything. So this is now galaxies, and what I explained about dark energy. So let's say that one right there, that galaxy. There's 1, 2, 3 on this side, and there is one there. These are like far away. the how far away it is probably also has an effect. So this galaxy probably is moving that way. And that's an easy way to understand dark energy. But of course, people can see that in astrophysics, can immediately test, observe how is that correct or not. Because the scientists can see which way galaxies are moving and everything. And it appears as if space is blowing up, expanding. But they're not all the galaxies are expanding. Actually, they're all expanding at the same speed, yes. But the only difference is if there is more galaxies here, then there is less here, then the math and geometry says that the galaxy is supposed to go that way. The Andromeda galaxy is going toward us, even if we're near it. But that is probably because behind it, there is a lot more galaxies that are pushing it. The outgoing masses of it are pushing it to go our way. So some galaxies even have an attractive force to each other and everything. 23% of space, scientists say, is dark matter. 73% is dark energy. But actually in my physics, all of space is dark energy, all of visible space. All of it is dark energy, because there is no place in the universe, visible universe, where there is no dark energy. Because wherever there is galaxies, all this space around them is dark energies coming out of them. Just when you observe it mathematically, there is billions of galaxies. So you gotta do the math and everything, and so on. Astrophysicists, they like to go into the details and everything. They even name all the galaxies and everything. But in astrophysics, I have written many pages and everything about suns, how they shine, about the math, about physics and everything. They believe that, let's say this is the Milky Way, and this is a neighboring galaxy. Astrophysicists believe, and they tell people, that the light from the suns in this galaxy reaches us in the Milky Way. I mean, they believe that a photon can go through a space like this, that's between galaxies. The little tiny photon, they believe, can go from here to here. This space right here is like minus 700,000 or something like that. People don't know that. The temperatures of space we know is in the galaxy and where the matter is. Right here where there is empty space, only thing people know about it is that it's dark. And the reason why it's dark, because there is no photons here. The images too are evidence of that. So there is no chance possible that a photon from one galaxy can go to the next. And when a telescope picks up images, it picks up pictures of light, but live pictures of light, but no photons. That is important to know in astrophysics. So if we are here, they believe that from the Andromeda galaxy, neighboring galaxy, a photon can go through the coldest space in the universe, where there is no suns, therefore it's very hot, very cold, extremely cold. Could be minus a million. Nobody knows that. Nobody's been there to measure it, of course. But some calculations say that it is so cold. I mean, when we go to the space station, their space is like minus 200 something, minus 300. But here, in between galaxies, it's like minus 700,000 and so on. Because there is no matter there, and there is no heat there at all. So, and to believe that a photon at the speed of light can go from one galaxy to the next is like even crazy to believe that. That's like so impossible, it can never happen. Explosions, even nuclear, like I explained. Energy only goes in light as far as there is heat. The moment the heat of a nuclear explosion spreads too much and the cool air around cools it down, the energy stops and the light stops. It's gone. So one thing I thought to point out, very interesting. So those are galaxies. And a scientist believes that a photon goes from this galaxy to that one. It's totally not possible, really. Because even in these images, people can see that a galaxy, the light is there in between its darkness. When we look up at the sky, we see one star, its light is that big around this darkness. There's no photons there. People would say, astrophysicists, it's invisible light or something like that. Invisible light, that's more like X-ray and things. A smart thing to know there that a light it cannot go through cold space, especially not between galaxies and so on. And then people realize that the speed at which images move through the galaxy, the age of the galaxy, then people see a correct math about that and about the age of the universe and so on. Because the speed of light, nothing goes faster than the speed of light, that's old way of seeing things. Not correct in space, and the space is not under such laws. That's just old stuff. That's what Einstein said, but how would Einstein know that is correct? Einstein wasn't in another galaxy or something, so how would he even know that, you know? And that was written like, what, 100 years ago? And people would, but okay, science is going forward step by step, you know. In 100 years, people will know 1,000 times better physics than people know today. Of course, that is for sure, one would say. So that's smart to know that sunlight and photons only go as far as there is heat of the sun. Once there is no heat or anymore, in its cold space, a photon does not go anymore. It is just an image of light that goes on and so on and makes the visible universe visible. And people believe that, some people in physics, that photons light comes into our eyes. But when you shine light into your eyes, it hurts your eyes. If actual photons come into your eyes. So then you realize that I see actually something else, actually, not something carried by photons. And even if photon of a distant galaxy could reach our galaxy, what are the chances that it hits the Hubble telescope? Pretty slim, because photons spread the farther away they are from the sun. So a photon coming from the galaxy, Andromeda galaxy, one would be in the Milky Way, another one would pass by it, because photons spread apart the farther away they are from their source. So, and even if it hit, let's say, the Hubble telescope, if that were possible, how can an image of the whole Andromeda galaxy fit in a photon? It's totally incorrect, and very smart to know that it's incorrect, and astrophysics just needs a new math. We are doing great with telescopes. Hubble telescope is doing good. New telescopes are always going, satellites and so on. So technology is doing good and so on. But the math and thinking, that's some of the problems in astrophysics and everything. But in future shows, there will be explanation of that. Sun's whole quantum distances of photons, it is called the butterfly effect, how the sun shine works. The omega effect and many things. The omega effect is just when a photon reaches cold space, it doesn't exist anymore. Yeah, there is invisible light, X-ray and so on, radio waves and so on, but when an image of a sun comes to us from a distant star or a distant galaxy, there's no photons in it. And it comes at a much faster speed than the speed of light, because it is not even carrying matter, it's carrying just images, information. So that's smart to know, you know. And in the end, I thought to mention, like, I mentioned nuclear physics and everything in the previous shows, and basically that's like some, you know, people add energy, fire into matter, and that's basically what it is, you know. And it's no big deal, like, yes, it was revolutionary physics in the past, but But this whole new way of seeing nuclear physics can lead to many, many more important things and better things and everything. And in many places and everything, you know, of course, you know, if it was us Europeans, us Christians, Western people and everything, and people would say, of course, well, we can talk amongst each other about nukes all the time, you know, why not? But many people will say then, our enemies will hear, these people will hear, yada yada. But I didn't even go into how nukes are made, just how they work and so on. But you know, that's sort of an old way of thinking. Many people go, like some politicians and everything, China's bad, Russia's always bad, and so on. You hear that in Western media and everything. But that is also sort of sticking to the old way of thinking, I think, you know. Russia wants to be advanced. They want a good life for them, for their people. Freedom is, people are more and more thinking about it and everything and so on, but there is freedom and everything, democracy, democratic government and everything, and Russia is a good place. People love physics, love science and so on. Russia has great scientists. And China too, you know, some people might say, you know, China has communism and they have some, but also in the past. Today, you know, they have, today's Chinese president seems like a relaxed person, okay person, isn't really all that about many things that are from the past, like some really tyrant way of thinking. And the Chinese people too, you know, they see China now as open, as free as the rest of the world and so on. Yeah, they have communism and some stuff, but Chinese too are moving forward to better way of seeing things and everything. In China, big problem is food. You know, half of the Chinese are farmers, you know, just to make the food for everybody and everything. So the food videos could help out a lot in China and everything from that point of view, you know. But many people in the West, you know, they're like, China's bad, Russia's bad, but that's more like just talk, you know. That's why when you observe this is very pretty, but these are images and everything. When you observe United States now, you know, Trump is president, and Trump is really the coolest president ever, you could say. Trump talks to Russians, Chinese, the North Koreans. Trump doesn't really give a shit about the past and everything. And past is past, you could say, you know. And and that's sort of because Trump, you know, he's many people are against Trump. They criticize him. He's betraying the people. He's betraying principles and something of the past and everything. But Trump doesn't care. He's a businessman, you know. Trump's a businessman, a ladies' man, because he sees people like people. Trump is a man of the people, I would say, you know. He's not a man of some other way of thinking. Trump's a man of the people. He sees people as people. So he talks to North Koreans, Russians, Chinese, everybody like friends, you know. And that's sort of like a nice, normal way of looking at things. You know. Many people criticize Trump. They're like, he's good with the Russians, he's good that. But globally, for the world, that's actually very, very good, you know. And that's what sets America apart from all other countries, makes America great and better from all other countries. Because a businessman, a millionaire who was just making money and chasing the best women all his life, he gets to become president, the most powerful man in the world. And a businessman, you know. And that's what sets America apart from all other countries. Because even a businessman can become president. So more freedom, more equality and everything. Not that just one establishment rules and that's that. Like China, for instance, you know, communists are ruling for the past like 50 years. But even there, nicer people are there to lead and so on and so on. So many people criticize Trump, you know, but Trump is like a man of the people. He sees it how he sees it, you know. But the old way was thinking, imagine if Hillary won. Well, it would have been more like something similar to the Cold War and something. Hillary, for instance, when she's talking about Russia, she's talking about this, she's all like that. Doesn't like Putin and everything and everything. So. But, you know, Trump won, basically, you know. The people see that we need a new way of looking forward. You know, not all the past. So past is past. Cold War has passed and everything. Yeah, there is some talk about, you know, one country doesn't want another country to become more powerful or something, but you know, when you realize that it's all about sharing and humanity becoming a greater place, which is sort of the physics that I'm writing and explaining. I mean, many things I just reveal. People might think why, you know, and everything. But the point of physics is to create, let's say, like a Star Trek society, a great society, a million times better than the one in the past and everything. And that's what physics and technologies are, like the internet and telephones and everything. Well, in the past, you know, people didn't even know Chinese. What Chinese is just somebody you hear stories about from merchants and travelers, and that was it. So you could just guess, you know, what the Chinese are. But now we live in the digital world. Whatever you want to find out about China, you can half of it see on YouTube, so, or on the internet and everything. Plus, all the people have information about each other. People are friends and everything. Everything sort of is globally going towards that, you know. The internet is like one technology that's all possible. Any imagination that a person has, any type of thinking, he can portray it on the internet. Make a video about it, make a text about it, or anything. So the internet is something that is very, very like a very big technology. YouTube, to me, is like one of the best ideas ever in physics. I mean, in technologies, as far as the internet. Because YouTube, whatever you want to find out, you just go on YouTube. And yeah, then you have to read between the lines and be a little bit more intelligent to figure out some secret stuff and everything. But you know, it's YouTube, So I think, you know, physics, we should go forward in creating the best civilization that is possible in the future. Best medicine, best food, best technologies, going to space. And I've been writing about that for years and years and everything. And I really like to share it and everything with people. And and that would be today's explanation about the galaxy and everything. And one big step forward is understanding that images in the universe and on Earth, they go faster than light, especially in the universe and everything. And it is much faster, much better, and that points towards technologies, the masses, the speed of masses, that can be Star Trek and everything. But when people believe nothing goes faster than light, then all that is lost. And it is old, and it's incorrect. I can prove it any day, so that is incorrect. I did experiments and everything before in the past and everything. So, like a photon going from one galaxy to the next, well, that's impossible. A sun couldn't go, it would cool down and be probably shut off if it was in too deep space, although some suns do fall out of the galaxies and everything. And they light up, but for some time and everything. So in the end, you know, to say that the universe is great and big and full of infinite possibilities, infinite technologies, infinite knowledges and everything, that I mean, people say that there is 120, 30 elements in the universe, and they try to understand the universe through that. But a neutron star is one atom, just neutrons and electrons, a magnetar star. So that's how big atoms can be in the universe. Some in the universe could be like as big as trucks on some distant planet. Who knows what can be in everything. So the Big Bang in part was like through little knowledge trying to explain something that's huge and endless and everything. Planets are dark matter. The Big Bang just explains, you know, they say it's hydrogen, then just through little knowledge of the like energy cooled down and then turned into hydrogen, yada yada, you know. But that's very little knowledge of 120 elements, and they try to explain the universe through that. So how would they explain trillions of planets and all the different matters on them and everything? Which is cold matter that they didn't even know existed, you know. So people can understand then about the universe that the Big Bang is really incorrect, you know. And basically that was some guy bored, didn't have what to do, and he started making some stuff up. Basically, because the universe is too big and too great to be explained through such little knowledge and everything. How the universe was created, an honest person can just say, hey, we weren't there when it was created, we have no idea. And that'd be okay. A religious person would say God created the universe, and that's what I believe, God created the universe. Just who God is, and that is beyond human comprehension and everything. God himself, the creator of the universe. Because God is too great compared to people, let's say. God creates the universe in 7 days. Takes us 40 days to make just a Ferrari, you know. Honestly, but then in religion too, many people go like, they know about God, even if they don't, and they like to believe that and so on. But God is too great and too powerful that people know a lot about God himself. So, but physics is showing, you know, the universe is showing that it is trillions of different things. There is thousands of different animals on Earth and everything. That some doctrine and some religious narrow-minded view of things just isn't really all that even correct, so to speak. So today's Easter, so in our country, we Orthodox Christians, we follow, today is Easter to us and everything. So this was like, I thought to do a nice Easter show that's long and explains many things about the universe and everything. And so thought to mention faith a little bit and everything, but when you examine, you know, I told some people before then everything, you know, I see religion also as a science. I don't see it as a religion. I see it as science and as seeing evidence. See, this is beauty beyond compare, like, and that's what God created, you know, the universe. But then some people with some little minds, they come over and they want to tell you like they know God's will. Well, how would you know God's will? Some dude in a cape or something, you know. But they read a few books and they think they're smart or something. In the show I even wanted today, didn't have time to make a religious show about the true faith. True religion, correct religion. I don't even call it a religion, but a faith, a belief that is correct. Christianity that is 100% correct. And the real understanding of faith and the ways of heaven and so. But that will be in future shows as well. So, and so in the end, I would say Happy Easter to anybody who is celebrating today as well. The Catholic in the West, they celebrated just 14 days earlier. That was just a difference in math, you know, of ancestors and so on. We both celebrate the same thing, which is resurrection and the living after death and everything. And the food, what I'm doing in part is to return the energy of youth into the body which is in a little tiny part like resurrection, being old and then being young again. So, and real physics and evidence is showing that and everything, that it's going well and so on. So that's all for today, and bye.